So today we have a very ambitious project. We're going to try to develop an FPGA based power analyzer in conjunction with the Cyclone 5 starter kit and the LTC2308 ADC converter. So I want to analyze the voltage and current input to the device, but I also want to measure the phase difference between the voltage and the current. And of course, if you know the phase difference, then you know the power factor angle and the complex power. But I also want to go one step further in this project. I also want to look at the harmonic content of my input signal. So this is going to be quite a challenge. Let's see how we can do it. Well, my starting point will of course be the ADC converter, which will be a 2-channel ADC converter. And I'm going to use the FFT, and that will sort of convert the time domain signal into the frequency domain. So I'm going to take the magnitude of the power frequency, that's 50 Hertz, for voltage and current, which is one of the key pieces of information I need. And then I'm going to try to send it through an embedded processor using the UART. More about that later. But I also want the phase, and for the phase measurement, I'll be using the CORDIC algorithm. And all that information, plus the harmonic content, will be sent over UART from the embedded processor into a graphical user interface. So there's lots to talk about in this project and lots to develop. Now, to be clear, what I want to send is the magnitude of the 50 Hertz voltage and current, the phase of the voltage and the current, and also the harmonics. Now, how far up in the harmonics we go, I'm not quite sure yet. We'll see how far we can push the FFT. And the FFT really will be the crucial part of this project. Now, the embedded processor is also very important to the way this project works, and we'll have a focus on how we can implement an embedded processor on the FPGA as well. So really excited about this project. Let's go to the agenda. So what I would like to do in this project is, first of all, outline the high-level architecture of the Power Analyser, interface to the ADC converter and verify with signal tap, implement 2 FFTs with full interface code, take the magnitude and calculate the phase of the output of the FFT with the CORDIC algorithm, design an embedded processor, and then output the results using the UART, and then finally we will write a Matlab graphical user interface with some nice pretty pictures so we can see the results from the Power Analyzer on the screen. And actually, because there's so much to talk about in this video, I've decided to split it into 2 parts. So in this video, I'll go up to and including the FFT and interface code, and in the second video, I'll talk about the embedded processor, and we can analyze the final results. So this is the block diagram schematic file of my Power Analyzer project. This is the top level entity, of course, and there's quite a lot going on here. So there's quite a significant amount of code in this project, but we'll take it one step at a time. And the starting point really, I think, is the ADC converter code, because that's fundamental to bring in the voltage and current signals into the design, and we have to get this right before we can make any further progress. So this is my phase locked loop. This is bringing in the 50 megahertz input signal from the Cyclone 5 starter kit board, and what it's doing is dropping down that frequency to around 10 megahertz. Now, the actual frequency of this clock going into the ADC converter is quite critical, so I'll address this in a bit more detail later. The second clock here is just 50 megahertz going to the rest of the design, so going to the embedded processor and other aspects of the design. But the ADC converter block is here. This contains the interface code for my ADC converter, and the chip we're using is the LTC2308, and this runs off SPI interface code. So the starting point really is to look at the timing diagram. And if we look at the timing diagram, we'll see that we have an input pin that carries the 12 bits of the sampled word, but because this is a serial A to D converter, they actually come in 1 bit at a time. This complicates our interface code because we actually have to pick off those bits 1 bit at a time to form the 12-bit word. We've also got this convert pin that initializes the conversion. Then we have the serial programming bit, and that programs the A to D converter into our chosen mode. And then we have the S clock to the A to D converter. So we're going to have a look at the interface code here. And another important aspect is we want a 2-channel A to D converter here. So we actually want to sample on 2 channels simultaneously, but it's not simultaneously. You have to do 1 sample per cycle, but we'll show you how to do that code. Now let's take a look at the LTC2308. So it's a 500 kilosample per second A to D converter of 12-bit resolution, and it has a maximum of 8 channels. We only need to use 2 of those channels, so our maximum sampling rate will be 250 kilosamples per second. Now, in terms of interfacing to this A to D converter, the first place to look really is the timing diagram. So let's take a look at the timing diagram. It's right at the end here. So this timing diagram is basically what we need to replicate in our interface code. Okay, so this conversion pin that will initiate the conversion for that cycle. We have the S clock, and what we need is 12 rising edges. Okay, so you've got various programming bits here, and we need to change these on each clock cycle to give us the appropriate bits for the configuration that we want for the A to D converter on that cycle. And we can also use these bits to change the channel. So because we need 2 channels, we will have to do some dynamic changes to these bits so we can alternate between the 2 channels that we need to look at. Now this bottom one is the actual 12 bits of that cycle. So you can see we've got 12 individual bits here, and we actually need to pick these off 1 by 1 on each clock cycle of S clock and construct our 12-bit word. And it's important to note here that this is a full cycle and we sample 1 word per full cycle. Okay, now the S clock, we can see that the maximum S clock that we can have is 40 megahertz, and that's significantly faster than our maximum sampling rate, and that's because we need many S clocks per cycle. Okay, and in our interface code we will have to produce a cycle like this and try to make these things happen once every cycle, and we can take 1 sample per cycle and move it to the next stage in the process. We can begin to look now at how to write this interface code, and the first thing I'll utilize is the cyclic nature of this code. And one of the things we can do is make a counter, an 8-bit counter, and that will give us 255 counts, or 256 if you include 0. So the first thing I do is let's have a cycle of 256 counts. And doing this allows us to look at what the value of count is, and then we can do specific things at specific times in the cycle. For example, we need 12 rising edges of S clock, but we only want that to happen for part of the cycle. We only need 12 rising edges, and our cycle is actually much longer than 12 clock cycles. So that's one of the first things we can try to do. And we can achieve this by having a convert variable. Okay, and we can say if convert is equal to 1, then make S clock basically alternate on each positive edge of input clock. So while convert is equal to 1, S clock will look like a clock. So we just need to make sure that convert is changing for 12 clock cycles, and then the S clock will switch on and off as desired. The next tricky aspect of this code is looking at how we pick off these bits one by one. Now this code is a bit more complex, and the first thing I'll say about this is the top here, every time count is 100, we will change the value of S0. And what that does is it changes the channel. You can see that from the table. Now the rest of the code is actually changing the convert variable that we discussed previously, and it's also picking off these bits one by one as they emerge from the A to D converter. So remember, you get 12 bits per cycle, but these bits come at you one by one, so we have to pick them off at the right time. And you can see the way we're doing it is we're actually storing it into a variable called data temp, which is an array. So each positive edge of the S clock, serial data will be read into the next bit of data temp, and that will construct our 12-bit word. Now we're also changing the value of the programming bit at this point. So S1, S0, unipolar, sleep, all those bits can be changed to exactly what you want using this code. And here I am in Signal Tap, and you can see I'm looking at the 4 pins associated with the A to D converter, including the S clock, the convert pin, serial program, and serial data. Okay, so remember, serial data carries the 12 bits of data. Serial prog carries with it the programming information to the A to D converter, and ADC S clock is of course the 12 rising edges. And by the way, if you're not using Signal Tap, then I highly recommend using it, because doing this kind of development is almost impossible without using Signal Tap. And if you're not sure what it is, it really gives you the ability to see the signals inside the FPGA in real time. So you can imagine how powerful this is as a debugging tool. And now I can see everything is looking as it should do. You've got the 12 rising edges, and then you've got the data, which kind of builds up this temporary array here, which makes up our 12-bit word. Another thing we can look at, this is, I guess, channel 1, and we can look at the next channel is going to be channel 2. So yeah, so this looks okay. Now the next step is to look at the A to D converter by sample, and that means I need a much slower clock. Okay, so the clock I use now should be the same as the rate at which the samples are coming out of the A to D converter. If I try to do it with this clock, it would be much too fast for the samples coming out of the A to D converter. Well, here I am in Signal Tap again, and this time I have a much slower clock. You can see I'm using the what I call the conv clock, and this clock is being generated by the A to D converter interface code, and it perfectly matches the rate at which the samples are coming out of the A to D converter. So this means we can actually plot one sample at a time in Signal Tap. Now I've actually got my FPGA development board connected up to my signal generator here, and that's producing 2 separate waveforms. Of course, in the real device this will be the voltage and current waveforms. But in the testing phase, I can use a signal generator, kind of makes sense. And I can actually use Signal Tap now to plot the waveforms as they come in. So this is a 50 Hertz waveform. And you can see that the sample depth I'm using here is 512 samples. I could probably do with going a bit larger than that to see more of the waveform, but this is 50 Hertz. And what I'm going to do now is, for one of the channels, I'm going to increase the amplitude, and we can see if that has an impact. So that's this one. So these two are the 2 input waveforms. And now I'm going to increase the frequency. Oh, that was actually on 40 Hertz, but let's increase the frequency. And you can see the frequency increase for one of the channels. So this looks pretty good. I think I can now move on to the next stage. For now, just ignore all this other stuff. This will be discussed in the second video, but this again gives you another example of where Signal Tap is really useful. Now, just one quick point here. Looking towards the next step, which is the FFT, we actually want the FFT to sample at the same rate as each sample is emerging from the A to D converter. And even though we have a cycle of 256 clock cycles, the actual sampling rate is once every 512 clock cycles, because we can only sample one channel every 2 cycles. So what I'm also doing in the A to D converter code is producing a much slower clock, which is feeding the FFT, and that will sample once every new data sample emerges from the A to D converter. Now let's talk about the next step in this project, and that's the FFT. Now, before I get to the FFT interface code, let me just say what our clock frequencies are. Now, the input clock to the A to D converter, I've chosen a frequency of 10.486 megahertz. Now, I realize that might sound very specific, but it's been chosen for a particular reason. Now, if you divide 10.486 megahertz by 1024, then you get 10.24 kilohertz. And I've actually chosen an FFT of a size of 2048 points. So what we're going to get actually from the FFT is a 5 hertz resolution. And that's important because we know one of our bins will fall exactly on 50 hertz. So what about the interface code for the FFT? Well, it's a case yet again of going to the timing diagram, and Intel publish a very nice user manual for the FFT Megacore. Now, luckily we've got 2 FFTs, but we only need to write one FFT interface code because it will be sent to both of the FFTs at the same time. So this is the timing diagram for the streaming FFT, and streaming means it will process consecutive windows without any pause whatsoever. So that's really convenient for what we want to do. And the way this works is you need a sync start of packet and a sync end of packet, and they represent the first and the last sample of your FFT input data respectively. So we have to make sure that they're separated by the required number of clock cycles, and then the FFT will start doing its job. And there will be a short latency period before the results of the FFT will start to emerge from the source output of the FFT block. Now, even though there's a latency period, that doesn't mean your output data is not continuous. It just means there's a short delay, a short latency period between the input data going in and the output data coming out, and that's usually very short, so it doesn't really matter that much. So what we need really is FFT interface code to give us the start of packet, the end of packet. We need to produce also the sync ready, sync valid, and inverse inputs, but they're just 1 bit and they don't really change. The challenge is the start of packet and end of packet, and with lots of Verilog code, the timing matters quite significantly. So as long as we get that timing right, we should be okay with this code. So back to the block diagram schematic file. Let's just keep track of where we are. So we've talked about the ADC interface code. Now we're on to the FFT interface code. You can see the block coming in from the A to D converter code. That's the slower clock. We've got the actual A to D converter samples going into this block. That just gets routed straight through here actually and into the FFT. And then the second input goes into the second FFT, and that's just going straight into it. Okay, so you can see we've got our 2 FFTs here, and as I said before, we only need to write one interface code for this because the interface is the same for both FFTs. The only thing that changes is this first FFT is for the voltage input, and the second FFT is for the current input. But let's take a look now at the code that we've written to satisfy the requirements of that timing diagram. And remember, the main challenge here is producing a start of packet and an end of packet which is spaced apart the right number of clock cycles. And as I said before, this is a 2048 point FFT, so we need to make sure that the start of packet and the end of packet are separated by 2048 clock cycles. So let's take a look inside this block and let's see the interface code. And it's actually very simple because all we have here is, again, another counter. Okay, so this is a 11-bit counter which should give us a count of 2048. And all we're doing here is looking at the value of the count. If the value of the count is 2047, we make sync end of packet go to 1. If the count is 0, we make sync end of packet go back to 0 and sync start of packet go to 1. And if count is equal to 1, sync start of packet will go to 0. This should give us the pattern of 1-bit signals that we need for the sync start of packet and sync end of packet. So hopefully this works. So in the context of the wider design, this interface code obviously is just before the two FFTs. This should give us the sync start of packet and sync end of packet that we need. And then the next step after that is to have a look at the signals coming out of the FFT, and that should contain the frequency domain information. So we'll have a look at that next. So that's really the end of the first part of this two-part series. And we've made some important progress in this video. We've written interface code for the A to D converter, and we verified in Signal Tab that that's bringing in those signals at the required sampling rate. Now we can certainly push that A to D converter to a much higher sampling rate if we need to later on, and that's always an option for us. But at least we've got something coming in now. I think we've got a 10 kilohertz sampling rate, which is fairly okay for what we need to do. Now we've also written some interface code for the FFT. So we've got a pair of FFTs, one for the voltage and one for the current. And in the next video, the first thing we'll do is analyze the output from the FFT just to see that the input signal is actually being split up into the frequency domain and the harmonics. Then the next thing we'll do then is try to take that information, so the harmonic information, the magnitude of the voltage and the current, and then try to pass it out of the development board using the UART into a graphical user interface. And we'll have a look in Matlab at writing a graphical user interface to visualize those waveforms, and that will be the end of the project. So I hope to see you in the next video and we will complete this project. Thanks for watching.